In the previous lecture, we talked about determining whether relationships are functions and one-to-one functions. So now we're going to talk about inverse functions. Now let me go ahead. I'm going to spend some time actually talking about inverse functions. And then at some point, I'm going to relate inverse functions back, especially to one-to-one functions. So at first, even though these topics are in the same section of the book, at first you might think they're not really related. Well, they actually are in one way, and I will get to that at some point in time. But I want to go ahead and define inverse functions, explain how to determine inverse functions. First, notation. Here's our typical function notation. F of x equals 2x plus 1. I am now going to write the inverse function of this function. So that is, if you're given a function, you can go determine the inverse of that function, and we call it the inverse function. So this is a function. What I'm going to write in a minute is what we call the inverse function. Now, in terms of notation, we know it's an inverse function when it's f of x, but up here it almost looks like an exponent, but it is not an exponent. It's just simply you put a minus 1. It's simply a way to designate an inverse function. This is not like a negative exponent. It's just simply a notation to say, hey, this is an inverse function. Now, as a matter of fact, I'm going to write the inverse function. If I have this function, the inverse of this function. Now, later on, I'm going to show you, if you're given a function, how to calculate or determine the inverse function. But for now, let me just give it to you. So now maybe you're asking, okay, so what's up with inverse functions? What are they? What do they do? Let me actually sort of write down a sentence that describes an inverse function. An inverse function reverses I think the easiest way to think about an inverse function is it's like it reverses what the function did. Another way to say inverse function undoes what the function did. And I'll just show you quickly here. So say we're given this function and we say we're going to calculate the function when x is 2, right? So f of 2 okay, when x equals 2, the function is 5. Now, just for fun, let's take that answer, the result of the function, and let's stick that in the inverse function. So really what I'm going to do is the inverse function of 5, which is 4 over 2, and you sort of ended up with what you started with. It's like one step forward, one step back. So I put x equals 2 into the function, I got a 5, then I took the result of the function, ran it through the inverse function, and then back to where I started. That's the whole idea. This inverse function in a sense, undid what the function did. The function took x equals 2 and gave me a result of 5. The inverse function took the 5, gave me back the 2. So in a sort of simple way of understanding, that's what an inverse function sort of does. Now, inverse functions, let's go back to our different kinds of relationships. So if you're given a set of ordered pairs and say it's a function, so let's say we have 0, 1, 2, 7, so first of all, here's a relationship. Is it a function? Look at the x's. 0, 2, 3, 4. Yes, it's a function. So we're calling this f of x. If you're given a function of ordered pairs, how do you turn that to an inverse function? Very easy. You swap x and y. So 0, 1 becomes 1, 0. 2, 7 becomes 7, 2. 3, 8, whoops, becomes 8, 3. 4, 9 becomes 9, 4. There's the inverse function. And the idea of reversing, say I choose x is 3 and I say, what's the function when f is 3? So I go here because here, this ordered pairs when x is 3. So it's 8. And then I say, well, what happens if I take the inverse function of 8? So now I go to the inverse function when x is 8. I'm back to 3. Now let me explain with ordered pairs, and this rule is going to also apply to graphs and equations, but I don't want to take the time to explain graphs and equations because the principle applies to both. And that's the idea about domain and range. Let's look. What if I say, what's the domain of f of x? Once again, with ordered pairs, it's just the x's, right? 0, 2, 3, 4. What's the range of my original function? Those are the values of y. So it's 1, 7, 8, 9. What is the domain now of my inverse function? So here's my inverse function. The domain are the values of x. So it's 1, 7, 8, 9. And the range of my inverse function, here's my inverse function, the range of the values of y. So it's 0, 2, 3, 4. So review quickly. Here's my function. I figured out the inverse function by swapping the x's and y's. Then I decided just to list the domain and range of the function, and then the domain and range of the inverse function. But if I look closely, look, here's the domain of the function 0, 2, 3, 4. If I go over here, look at the range of the inverse 0, 2, 3, 4. Matter of fact, if I look at the range of the function 1, 7, 8, 9, Look at the domain of the inverse, 1, 7, 8, 9. Here's what happens, whether it's ordered pairs, a graph, an equation. The domain of the original function is going to equal the range of the inverse function, and then the range of the original function is going to equal the domain of the inverse. It's like they get swapped. So that rule is going to apply ordered pairs. Now here, let me show you one more thing. I'm going to prove it to you with ordered pairs, but the same principle applies with graphs and equations. Now here's where it's interesting, and here's where a one-to-one function sort of relates to inverse functions. Let me go and state the principle or the rule, and then we'll go and show it to you. You can have, let me say it like this. Say you're given a you have a function, and then you find the inverse function. And once again, I'm already warning you, I don't like this language, but it is what it is. So you're given function, and you determine or calculate or find the inverse function. Now the question is, when you determine this inverse function, is this inverse function really actually a function? I started with a function. In other words, I started with something that obeys all the rules about being a function. But when I take the inverse, is the inverse a function? So let's do a simple example of ordered pairs. I'm going to give 3 ordered pairs, and it's going to be a function. Right? If I say, is this a function? Do the x's repeat? They do not. It is a function. Now, let's calculate the inverse function. You simply swap the x's and y's. Is the inverse function a function? Well, you see, you asked, did the x's repeat? X is 1, x is 1, boom. You know what? X is repeated. Turns out the inverse of this function is actually not a function itself. And that can happen. You start with the function, you take the inverse, and the inverse, so I could say, I could be careful. Given a function, determine the inverse of the function. Doesn't say it's a function, it's the inverse of the original function. And then you say, okay, once you take the inverse of the function, is that a function? Here's an example. You have a function, inverse, it's not. Let's do another one. It's going to look the same. 0, 1, 2, negative 1. You'll notice I've changed the thing that's causing a problem. So here's my function. Is it a function? Yes. x is 0, 2, and 3. Is it an inverse function? Let's find the inverse of the function. So I just swap these. Now, is this a function? Check the x's. 1, -1, 3. Yes. So in the second case, we have a function, and the inverse of the function is also a function. Now, you know what we can say? We can actually look at a function, and before we even calculate the inverse, we can determine if the inverse is an actual function. You know how we know that? The inverse of a 1-to-1 function what you do is when you have a function and you're going to take the inverse and you're wondering before you even take the inverse, okay, when I take the inverse, will the inverse of the function also be a function? Before you ever even calculate the inverse, you can determine it. And what's the key? You go look at your original function. You say, is my original function a 1-to-1? If it is, then I know, without even doing it, I know the inverse is going to be a function. So if you're given a function and you're asked, is the inverse of this function a function? All you say is, you go look at the function, is the function a 1-to-1 function? If it is, you can say, yes, the inverse is going to be a function. If it is not a 1-to-1 function, then you can say, no, the inverse is not a function. Let's look at our example up here. Our first one, is f of x a function? 0, 2, 3. Yes, it's a function. Is it a 1-to-1 function? Remember 1-to-1 function? No x's repeat, no y's repeat. No x's repeat, it's a function. Is it 1-to-1? Check the y's. 1, 1, 3. The y's repeat. This is not 1-to-1, which means when you take the inverse is not a function. The second, is it a function? 0, 2, 3, yes. Is it a 1-to-1 function? Now check the y's. 1, -1, 3. This one is a 1-to-1 function. That means I could say at this point, when I go take the inverse of this function, it is also going to be a function. And it is. Look at the inverse. 1, -1, 3. It's also a function. So the way that 1-to-1 functions tie in with inverse functions, the big way is, if you have a 1-to-1 function, you know the inverse is also going to be a function. So now let me finish out by talking about, we talked about ordered pairs, how to find the inverse function. How do we find the inverse function given a graph? It's not that hard. It's a little tricky at first, but not too bad. So your function's a graph. How do you figure out the inverse function of a graph? And what you do is, let me write it down here, then I'll show it to you. We're going to do a mirror image around the line y equals x. All right. Obviously, that's not going to mean a thing. So let me show you. Here's my function. I want to go ahead and also graph the inverse function. Here's what you do. Mirror image around the line y equals x. Remember mirror image with graphs? So sometimes, a lot of times you have a mirror image around the x-axis, the y-axis, where it's like if you rotate it halfway around, it's like a mirror image. I'm going to do the same. So for instance, you know, say I want to do a mirror image, I want to rotate this graph around the x-axis, then it's almost like you flip it over and here's your mirror image, right? If you want to do this, a mirror image around the y-axis, then it becomes maybe hard to draw. Right? It's like you flip it. Well, in this case, if we're given a function and you want to see what the inverse function looks like, you do a mirror image. This line right here represents y equals x. It sort of splits the first and third quadrant in half. You do a mirror image around this. So it's almost like you take this thing and you flip it over here. Now sometimes it's easy to visualize it. If you have to actually be precise, what you can do is you take a few points, like say if I think this point here is like 1, 2, 3, 4, if that's 0, 4, if I go over here and I reverse those and I go plot 4, 0, this is going to be on my inverse. Say I've got this point right here, say 3, 8. If I go plot 8, 3, 5, 6, 7, 8. If I go plot 8, 3, it's going to be my graph. If I do one more, if I do this one right here, negative 5, 0. And if I go plot 0, negative 5, all right, you can easily draw in the mirror image. I just wanted to show you, in case you ever needed to be precise, how you could actually come up with some points here. So this right here is the inverse. All right, with graphs, not too bad. You'll get the hang of it. You can see it pretty easily in the homework. Now the last one. If you're given an equation as a function, how do you find the inverse? And here, there's actually some steps you go through. It's not too difficult. Let me actually write down the steps and do a couple of examples, and I think you'll see it's not that hard. So for instance, I'll give the steps and I'll do an example. How about I'll just do the one I started with way back at the beginning. That first function I gave you was 2x plus 1. We want to determine the inverse of that function. First thing I do to make it easy, I'm going to replace f of x with y. You'll see why in a minute why that makes it easy. Of course, f of x and y are really the same thing, so this is not anything too crazy. So I got y equals 2x plus 1. Now, I want to actually go in and swap my x's and y's. Excuse me. So that means instead of a y here, I'm going to put an x, and here I have 2x, I make that 2y. So every place you have an x, you make it a y. Every place you have a y, you make it an x. Once you do that, now you're going to solve for y, which means you want to get y by itself on one side. So here, if I want to get y by itself, subtract 1 from both sides, then divide both sides by 2. Now I've solved for y. Then the fourth and final step is replace y with the inverse function notation. Then you simply say, therefore, and if I go way back at the beginning of this lecture, I said, here's my function, and then I just gave you, I said, hey, this is the inverse function, x minus 1 over 2. Well, here, I showed you how I came up with that. So hopefully, you'll see it's not too hard, actually, if you're given an equation, to calculate the inverse of the function. First of all, you replace f of x with y, then swap the x and the y. Let me do one more example, a little more, the algebra is a little trickier. You may see something like this in the homework. So here's the function x plus 1 over x minus 2. And they want us to determine the inverse function. First step is replace f of x with y. Next step is swap x's and y's. So this becomes x equals y plus 1, y minus 2. And now I need to solve for y. Now this is a little trickier than the last one because I've actually got two y's here. Matter of fact, what I'll do first is let's multiply both sides by y minus 2 to get rid of this fraction. So if I multiply out this side, you get xy minus 2x equals y plus 1. Now if I want to solve for y, if you remember your algebra, I need to get all the terms with the y on one side and every term without a y on the other side. So I'm going to, anything that has a y, I'm going to move to the left-hand side. And if it does not have a y, I'll move to the right-hand side. So hopefully you can see I'm going to subtract y from both sides. And then I need to subtract or add 2x to both sides. So this is just some basic algebra. So now, all the terms with the y are on the left-hand side. The terms that don't have a y are on the right-hand side. My goal is to get y by itself, so I'm going to factor out the y here. And if I want to get y by itself, if I divide both sides by this whole parenthesis, then I get y equals 1 plus 2x over x minus 1. And then now it's a matter of simply replacing this y with my inverse function notation. So for f of x equals x minus 2, the inverse function is 1 plus 2x over x minus 1. Now you're going to have some problems where I'm warning you, this principle of the domains and ranges of the functions and inverses, they just sort of swap. Let me do one quick example. Actually, I'll just use this one. Let me just look at the domain. Well, I can look at domain and range. So, to start out here, what would the domain be of this function? Well, in this case, the only thing I have to worry about is I can never let the denominator be 0. So the domain is all real except x cannot equal 2. Turns out the range is just all real. There's no limitation. Now, without even doing the inverse, the principle says the domain of the inverse should be the range of the function. Should be all real. Now, I'm going to see if it looks like it checks out. And the range of the inverse function is the domain should be all real except x cannot be 2. Let's see if this is true. Let's actually go look at the inverse. Here's the inverse. What would be the domain of this? Well, x cannot be equal to 1, so the domain would be all real up looks like I'm either confusing myself or misunderstanding. Let me talk through this again. The domain of the function is x cannot be 2. Oh, you know what? I think my problem is I assumed my range was R real, but I guess I cannot. You know what happens if you graph this? Here's my mistake. See, I tried to do this on the fly. I think if you graph this, you have, I think the graph looks like this. Actually, y, I think y never equals 1. So the range is all real except y cannot equal 1. I don't expect you to know this. This is just the example I chose. So therefore, now the domain all real except y cannot be 1, and I go look, and the domain x cannot be 1. The domain, that's true, x cannot be 1, and then the range, it's going to be the same thing. It's hard to look at. Anyway, unfortunately, I tried to do an example on the fly, and it became a little more convoluted. But the principle is the same. Once you have the domain and range of the function, they just swap to get the domain and range of the inverse. So even though this is a poor example, I did it on the fly, the principle still applies. So All right, so that's inverse functions.